Unit 9 is all about rational functions, and 9.1 is our introduction lesson. So, going over some key terms, a rational function is an equation of the form f of x, or remember that could be like a y, equals p of x divided by or over q of x, where p of x and q of x are both polynomial functions, and q of x cannot equal 0. Basically what that means, it's any time where you can have an equation, I'm going to write it out as like y equals something up here, so some number over some number. And these two numbers can both be expressions that have x. So maybe this is 1 and this is x minus 2 or something like that. Y equals 1 over x minus 2. That's an example of a rational function. As long as there's something divided by something else, and the thing on bottom cannot be equal to 0, because we can't divide by 0, that would be a rational function then. So let's go on to excluded value. That's any value of a variable that results in a denominator equaling 0 in a rational function. In this example that I've made, if x were to be 2, 2 minus 2 equals 0. And we can't have something being, or we can't have our denominator equaling 0 here, because then it'd be 1 divided by 0. And you can't divide by 0. So this number here, 2, would be an excluded value. And the last term is called an asymptote. An asymptote is a line of the graph of a function that it'll approach, but it'll never actually touch. So it gets very, very close to a certain line, but it never actually touches that. And we'll go over how to find these asymptotes and how to use them to graph the functions in just a little bit. First, let's go over how to find excluded values. So our examples say state the excluded value for each function. In this function, we've got negative 2 over x. Now this negative on the outside can be applied to either the top or the bottom. Normally it might be easiest just to apply it to the top. So we can simplify this whole thing and just call it negative 2 over x. Now, in either case, if we called it x on top or the negative on top or negative on bottom, what we have is a denominator of x. Now to make our excluded value, we just set our whole denominator equal to x, or equal to 0, and then solve for whatever x would be. In this case, we can just say x cannot equal 0, because we do not want this denominator equal to 0. There's no solving left to do, because we already have x alone, so that would be our excluded value. We cannot have a spot where x equals 0. Let's do another one. In this case, we've got x over 4x minus 8, and then all of that we subtract 1 from. Now in this case, this subtract 1 doesn't affect this denominator. So, like the last one, we just take our denominator and say that it cannot be equal to 0. 4x minus 8 cannot be 0. If this equaled 0, we'd have something divided by 0, and we can't have that. So the denominator we just set not being able to be 0, and now we solve for x. In this case, we would add 8 to both sides, and we would get 4x cannot equal 8. And now we need to divide both sides by 4 to get x alone, and we would say that x cannot equal 2. So in this case, our excluded value is 2. That is the spot where x cannot be. If x were 2, we would have a divide by 0 on bottom there, and that wouldn't work. Identifying and using asymptotes to graph rational functions. Any rational function of the form y equals a over x minus b plus an extra c value has a vertical asymptote at the x value that makes the denominator equal to 0, or you can think of it as x being b, and there's a horizontal asymptote at y equals c, so this extra value here. Now notice, this one, x equals b, makes a vertical line. This one, y equals c, makes a horizontal line. And in our examples, you'll see what those look like. Note, the domain of a rational function is all real numbers except for b. So in this equation, x can be any number except for this number b. The range is all real numbers except for c. So y can come out to any value except for this value c. Rational functions cannot be traced with a pencil that never leaves the paper, so choose x values on both sides of the vertical asymptote to graph both portions of the function. And again, you'll see what that looks like as we go through our examples. So, first off, in example 3, we need to identify the vertical asymptotes and horizontal asymptote of each rational function. Then we'll make a table of values to sketch the graph of each function. Now our hint for this is always to use one value really close to the asymptote, then go 3 in the opposite direction. So you should probably add an extra box to the end of your table here. That way we can have 4 to the left of it and 4 to the right of it. So in our example, we have f of x equals 2 over x plus 2. Now what value of x would make this equal to 0? Again, if it helps, just do the cannot be equal to 0 and solve for x. In this case, we would have x being negative 2. That would be our excluded value. That is where we cannot have it. So our table is going to center around negative 2 right here. Our horizontal asymptote, what is the c value that's added on over here? Well, it's like there's a hidden 0. So our horizontal asymptote is y equals 0. I'm going to draw these lines onto our graph right now. Here is our y equals 0. It's just our x-axis. All of these values here have y being equal to 0, and our graph will never touch that line. Here we have our vertical asymptote, x equals negative 2. Again, all of these values on here, x can never be that value on this line. So our graph will get really close to these two lines, but will never touch it. So now, let's find some values we want to use. First off, in the very middle of our table, we use values really close to negative 2. So I'm using one that's a little bit smaller than negative 2, so negative 2.1, and one that's just a little bit bigger than negative 2, so negative 1.9. Going in the opposite direction, getting even smaller, I'll use numbers like negative 3, negative 4, and negative 5. So I've got 4 values that are all to the left of this line. Now, I went one that's a little bit bigger as well, this 1.9, so I'm going to use values that are even bigger than that, such as negative 1, 0, and 1. So now I've got some values that are to the right of this line as well. Now all I do is simply take my calculator and plug in these values into this function. Now this is how it will look when you plug it into your calculator. Start with this number 2 divided by, because it's a whole piece on bottom that you're looking for, put it in parentheses and do negative 5 plus 2. Because negative 5 is your x value, or at least your first x value, and then we're adding 2. When you do this, your calculator should give you negative 0.66, which is about, is exactly negative 2/3. So we'll have to plot a point there. The only thing you change each time you plug it into your calculator is this red number. Instead of being negative 5, next to negative 4, negative 3, negative 2.1, and so on until you complete the table. When you do that, you should get these values. Now all you have to do is plug these in on the graph. So we go to where x is negative 5 right here, and we're down at negative 2/3, so about right there. We'll do it again for negative 4. We are at negative 1. For negative 3, we'd be at negative 2. And starting to get really, really close to this line, we'd be at negative 2.1, is at negative 20, so somewhere way down here. Now notice, these 3 dots cannot cross this line or this line, because we cannot have points that are on those. So, as we start to graph these, we'll start somewhere around here, draw our line, make sure to go through this point, and this point, and it gets really close and it'll give us some kind of swoop that looks like that. This almost looks like a parabola, but it gets very, very close to this line without ever touching it. Swoops away, and over here gets very, very close to this line, but again, still never touches it. On the other side of this line, let's use numbers like that negative 1.9, which is just a little bit to the right of this line, is up at negative or positive 20. So somewhere way up here. When we are at negative 1, so right here, we're up at y is 2. So this point. When we're on 0, x equals 0, we're at the value 1. So right here, and we're at x is 1, then y is up at 2/3. Again, you can kind of see from this point to this point to this point to this point, it has kind of a nice steep swoop and continues going on in this way. So we'll just connect these values, coming down, and swoop away like that. Now this will get very, very close to this line, but it'll never touch it. Same thing going in this direction, will get very, very close to this line, but never touch it. These two red lines are the graph of our rational function. Again, they kind of look like two parabolas, but it's two swooping lines that never actually touch these green asymptotes. And that would be how to graph that function. Let's do this process again. For example 4, we've got the function f of x equals negative 1 over x minus 2, all of that adding on 1. Now again, to find our vertical asymptote, that's the value that would make this denominator equal to 0. So what you would do is say that this thing cannot equal 0, and then solve for x. So we'd have to add 2 to both sides, and we'd have that x cannot equal 2. So our vertical asymptote is at x equals 2. I'm going to draw that on our graph right now. I'm going to use a thinner line though. Here we go. So this green line, x equals 2, that is our vertical asymptote. Our line or our graph will never cross that value. Now at the end here we have this plus 1, so our horizontal asymptote is y equals 1. So here we go. There is our horizontal asymptote. Again, the lines will never cross these two asymptotes. That'll help us to graph. From here, if 2 is our vertical asymptote, then the points on our table should center around 2. So one that's a little bit bigger than 2 is 2.1. One that's a little bit smaller than 2 is 1.9. Getting even smaller, we would use 1, 0, and negative 1. Getting even bigger, we would use 3, 4, and 5. These values then would get plugged into this function. And again, this is how you might type it in on your calculator. Because we need all of this rational part first, and then add 1, we open up a parentheses first. So that's this piece and this piece. Now we have a negative outside of it that we can apply to either the top or the bottom. To make it easy, let's apply it to the top, and we'll call it negative 1 on top divided by x minus 2. As you type that in, that says negative 1. Then you say divided by, and then in parentheses, negative 1 minus 2. We use negative 1 because that was our first value here, and minus 2 because that was this operation. And we close our parentheses to say that we're done with this rational part. At the end, we just add 1, like it says to do with this piece. When you hit enter then to solve it, it should give you 1.33, which again is about 1 1/3. So as we plot that on our graph, we go to where x is negative 1, and we'd be at y is 1 1/3. So right about there. Plotting in the rest of these into your calculator, again, the only thing you're doing is changing this red number here so that it is 0, then 1, 1.9, and so on. As we do that, that should give you these values. So you would just take and plot those individually, where x is 0, y is 1.5. So we're at 0, 1, and 0.5, or 1.5. When x is 1, y is 2, so 1, 2. When x is 1.9, so really, really close to this line, we're up at 11. So we're right about there. So again, you can kind of see the swooping nature of this graph. Let's start here, come down, swoop through those, and again, we're getting really, really close to this line, but we're technically never ever touching this line. It's going to continue to go up in that direction, continue to go left in that direction, never touching these lines, getting very, very extremely close, but not actually touching it. Let's do the other side of our vertical asymptote, everything to the right, where we have x is 2.1, so kind of right next to this line, we're at -9. So that's right here. Where we're at x equals 3, we're at 0, so this spot. Where x is 4, we're at 0.5, so we would be right here. And where x is 5, we're at 0.66, or 2/3, so just a little bit closer than that last one. Again, looking at our points, we can see that swooping nature. We come up like this, cross through those points, swoop through there. Again, getting very, very close to this line, but never actually touching it. And that completes our graph. We have the two swoops. Again, as we go left, never touching this green line. As it continues to go up, it's never going to cross this green line. It picks back up on the other side of this line, getting very, very close, but never touching it. Swooping away this way, getting very, very close, but never touching this horizontal line. So we have our two swooping lines that make the graph of our rational function here. And that'll be it for our first video.